Hello, my name is Isabel Aldahir, and welcome to my talk on the influence of surface electric fields on the chemical passivation of silicon oxide interfaces after firing. So as many of you will already be aware, the surface of silicon is particularly prone to defects known as interface states, and these act as recombination centers. One very common method to mitigate this problem is to deposit a dielectric on the surface to reduce the density of interface states, and this is termed chemical passivation. Often working alongside chemical passivation, we have field effect passivation, and this is where either an intrinsic or an extrinsic charge is applied to accumulate one type of charge carrier at the interface whilst the other is repelled. And this reduces the probability of recombination occurring at any remaining interface states. So this brings us on to the question at hand: can a surface field influence chemical passivation? In this work, we are using an industrially prevalent dielectric stack of silicon oxide and silicon nitride upon N-type silicon. Silicon nitride is very well known to possess a relatively high intrinsic positive charge, as well as a substantial hydrogen concentration, which is introduced during deposition and which is reported to be most stable in the positive charge state at the silicon oxide interface. Now, in earlier work, changes in surface passivation and interface state density has been observed as a result of strong electric fields provided by corona charging. And here in this work, we want to compare our observations on this particular structure to determine how surface fields impact the chemical passivation, most likely due to influencing the presence of hydrogen at the silicon oxide interface. In this work, two types of wafers were used. Both were low resistivity N-type silicon. However, set A was plain afloat zone and set B was textured Czochralski. Both wafers underwent thermal oxidation, set A to a thickness of 100 nanometers and set B to a thickness of 5 nanometers. Following this, silicon nitride was deposited upon both sets. Set A used an open-load PECVD to deposit a single layer of thickness 65 nanometers and a refractive index of 1.9, whereas set B used an LPCVD tube furnace to deposit a double-layer silicon nitride, where the first layer was of 5 nanometers and a refractive index of 1.95, and a second layer was 60 nanometers with a refractive index of 2.2. Subsequently, positive or negative corona charge was applied to the front and rear surfaces of both sets A and B, followed immediately by a high-temperature anneal. Firstly, on set A substrates, we evaluated how the overall passivation depends on field polarity. Here, the blue bars represent the lifetimes of an oxide nitride control prior to any processing, and these lifetimes are typically around half a millisecond. The red bars represent the lifetimes after we add 10, 20, 30, or 40 seconds of positive or negative corona charge, followed by annealing. This is termed a corona anneal. And the yellow bars indicate the lifetimes after we perform an additional corona anneal to see if we have yet maximized the passivation. And so we determined that annealing in the presence of positive surface fields shows a substantial improvement in effective lifetimes, whilst annealing in the presence of negative surface fields showed reductions. Now, these results are not at all surprising or unexpected on N-type silicon. However, what is not immediately clear is whether these changes in passivation are predominantly due to field effect or chemical passivation. And so in order to determine this, we performed a study of the electrical properties of the interface. So for set A substrates, we take our specimen and we apply P.PSS to the front and rear dielectric surfaces. P.PSS is a transparent conducting polymer, and in this setup it serves as our gate electrode. We can then place this onto the Sinton lifetime tester, make a contact to the bare silicon as well as to the front and rear gates, and this enables us to bias both dielectric surfaces whilst simultaneously taking lifetime measurements. On set B substrates, since P.PSS doesn't apply well to textured surfaces, we used incremental additions of negative corona charge to serve as the gate on both the front and rear surfaces. We could then take lifetime measurements of the corona charged specimen where the concentration of corona charge was verified using Kelvin probe. For set A, we determined the effective lifetime as a function of gate bias for different types of process specimens. Here, the minimum point on the y-axis is a strong indicator as to how good the chemical passivation is for each type of specimen. And we can quantify the chemical passivation and the interface properties by modeling these curves using Shockley-Hall statistics. Here, the interface charge of each specimen was determined from the location of the minimum point on the x-axis. These values can also be corroborated using capacitance voltage measurements. We also determined the charge fluctuations within the dielectric, and by adjusting the electron and hole capture rates as well as the density of interface states, we can accurately model our experimental data. The full list of modeling parameters is provided in the proceedings paper. And so we determined that if we annealed the oxide nitride stack in the presence of a positive surface field, there was little to no change in the chemical passivation. The density of interface states remains constant, approximately 1 times 10 to the 10 relative to the control, and the electron hole capture rates do not vary substantially. However, annealing in the presence of negative surface fields showed an increase in density of interface states from 1 to 10 times 10 to the 10, and the electron hole capture rates increased by about 2 to 4 times. Therefore, here we can state that there is a field-dependent and a polarity-dependent effect on chemical passivation. We then repeated this experiment on set B substrates, here using corona charge as the gate as mentioned previously, and we determined that our results on set B substrates were in contrast to those on set A. Here, annealing the oxide nitride stack without any extrinsic field present, just relying on the intrinsic positive charge within the nitride film, resulted in a worsening of the interface passivation. Here the density of interface states increases from 2 to 8 times 10 to the 10, and the electron hole capture rates increase by about 4 times. Annealing in the presence of an extrinsic positive surface field resulted in similarly poor levels of chemical passivation. On the other hand, annealing in the presence of a negative surface field showed that the same high levels of interface passivation are maintained as the control, as the density of interface states remains constant at approximately 2 times 10 to the 10. And strengthening that negative surface field prior to annealing resulted in improvements to the interface passivation, as the density of interface states drops from approximately 2 to 1 times 10 to the 10, and the electron hole capture rates lower by about 40%. Therefore, these results are in contrast to those of set A, where negative surface fields showed degradation, whilst positive surface fields showed little change. We then repeated this experiment on set B substrates. However, firing was now done at 600 degrees Celsius, and we applied a range of positive and negative field strengths prior to annealing. So starting from left to right, we found that again, if we annealed the oxide nitride film without the presence of any extrinsic field, there was a worsening in the chemical passivation. Here, the density of interface states increases from 2 to 3 times 10 to the 10, and there's an approximate doubling of the electron hole capture rates. Annealing in the presence of positive surface fields similarly showed worsening of the chemical passivation. Here, in all cases, the electron hole capture rates increased substantially, and under medium and strong surface fields, the density of interface states increases compared to the oxide nitride control, up to a maximum of 4 times 10 to the 10. Annealing in the presence of negative surface fields showed a trend where the stronger the negative surface is prior to annealing, the better the resulting interface passivation, as the density of interface states continuously drops from 3 to 2 to 1 with increasing field strength. These results show a similar trend to those performed at 450 degrees Celsius. However, here the reduction in passivation under positive surface fields is less severe than at 450 degrees Celsius. These results lead to 2 main questions. The first question is, why is there a contradiction between the results of set A and set B, despite the fact that we are using very similar structures? One very likely possibility could be that the properties of silicon nitride are crucial in how hydrogen behaves. The refractive index of the film, and therefore the density of the film, influences hydrogen's mobility. Additionally, it's been reported that within higher refractive index films, there's a tendency for hydrogenated complexes to form, and therefore higher firing temperatures are required to mobilize atomic hydrogen rather than these hydrogenated complexes. Another explanation could be the difference in thickness of the oxide films on set A and set B. However, we observe no evidence of dielectric breakdown even on the thinner 5 nanometer oxides of set B, and so we discount this as a plausible explanation for the changes in surface passivation and defect density. The second question is, what mechanism is responsible for the density of interface state's dependence on surface field? One possibility is that hydrogen is diffusing into the bulk of Czochralski silicon in set B substrates under positive surface fields, and is interacting with oxygen clusters that are generated at high temperatures within Czochralski silicon. And so it could be that we are observing the effects of interface depassivation as the hydrogen diffuses into the bulk of the silicon, and therefore it's quite possible that negative surface fields are responsible for retaining the hydrogen at that interface and preventing that indiffusion and depassivation from taking place. Lastly, it's been reported that hydrogen generated by corona charges themselves are capable of introducing interface defects. This has been reported on silicon oxide structures under very strong positive and negative corona electric fields. Therefore, in conclusion, our results have shown that surface fields do influence the chemical passivation. We observed that on set A specimens, positive surface fields showed little to no change in chemical passivation. However, negative surface fields showed degradation and an increase in the density of interface states. In contrast, set B specimens showed the opposite trend, where negative surface fields showed improvements to passivation, whilst positive surface fields showed degradation. Therefore, future work is required to understand and explain the mechanism behind the interface's response to surface fields. Thank you very much for listening to this presentation.